Hi, I'm Michael Sun, and I'll be talking about my ICML Spotlight paper, representing molecules as random walks over interpretable grammars. Molecular discovery has gained significant attention within the AI community. It is a very important problem, with expansive applications in drug development, materials discovery, renewable energy, agriculture, environmental engineering, and much more fields. Small molecule discovery is especially ripe for intervention of AI because there is large chemical space, estimated to contain at least 10 to the 60 small drug-like molecules, and there exist strong incentives from industry to search within this space for new drugs and therapeutics. We now have huge datasets containing over 10 billion small organic molecules, enabling the rampant adoption of generative AI. However, there has been less attention paid to discovery of large molecules that exhibit structural motifs, and these define chemical classes like polymers. The main reason why progress is not caught on is because these domains contain as few as 100 examples but has more complex designs, with molecules having hundreds or more atoms. Considering the wealth of applications across materials science, agriculture, environmental engineering, and more fields, it is essential to bridge the gap between traditional expert-based approaches in this setting and modern learning-based approaches. First, I will talk about how experts traditionally design new molecules in this setting, and then introduce our workflow, which combines expert input with machine learning. In this setting, the tried and true way is to hand design new molecules using knowledge of known functional groups and then referencing the current state-of-the-art designs for ideation. This involves composing together functional groups which are standalone motifs that exhibit desirable properties. This also involves recognizing patterns over how the best designs are composed from these building blocks. It is an extremely expensive process that requires someone with deep domain expertise and extensive experience in the field to ideate new designs, then iterate on them. Our work follows this expert-based paradigm, and in addition, we answer two questions in a novel way. The first question is, where do we obtain these motifs? And the second question is, how can we compose motifs together? Our workflow has multiple levels of expert involvement to answer these two questions, given from an expert-dominant approach to an entirely automated approach. The output of our workflow is a set of motifs and a set of representations of the best existing designs over these motifs. First, we'll describe the expert approach. In the expert approach, we or the expert compile the set of motifs which are known to be good. We also ask experts to provide us annotations for the attachment contexts, highlighted in red. These contexts explicitly specify what needs to be present in the neighboring group in order to attach it to the current functional group. As an example, we show 4 functional groups from the gas separation membrane domain, and these are known to be good by experts in this domain. After these motifs are compiled and the contexts are annotated, we can then annotate the occurrences of these motifs within existing designs. This allows us to segment the molecule into these motifs, and this allows us in turn to represent existing designs using these motifs as the basis. As a note, there can be some offset between what our motifs can actually compose and the actual design found in literature. So we try to find the representation which allows us to most accurately depict the existing designs. Now, when the compilation of motifs is not present at the start, we obtain a data-driven approach to extract these motifs along with building the representations of existing designs over these motifs. The way we do this is as follows. We ask experts to fragment existing molecules by simply identifying the bonds to break. After breaking the bonds, we obtain a set of fragments that ideally correspond to meaningful functional groups. We then ask experts to specify rules for inferring the context for each motif. This rule is decided based on the domain and the expert's design considerations. For this example, the expert chose to break the bonds between 3 and 5, 8 and 9, 12 and 13. The rule is to pick a neighboring ring as the context if it does not touch a ring in the fragment itself. Otherwise, pick a single atom to be the context. In this example, the leftmost first fragment has the highlighted ring as the context, and the second fragment has two contexts, each being a single atom. Lastly, even in the absence of an expert, our workflow can still run by using existing algorithms to fragment a molecule. And this can be based on either simple heuristics, which is one of our baselines, or based on synthetic accessibility as used in algorithms like RDKit's bricks. However, the performance is maximized when we can incorporate expert knowledge to the maximal extent. One reason is that specific larger motifs contribute more inductive bias to our representation. In this example, we see the expert likes to keep the motif in B1 and the motif in B3 together. But a heuristic algorithm will further break those down until it cannot anymore. Now, we describe what the grammar in our work refers to, motivated by the way we have processed the data. Our grammar is implemented as a motif graph, where each node is a motif and random walks can be traversed to construct different molecules. Each node in this graph keeps both the base fragment and the context fragment highlighted with red. For example, motif 5 is a carbon single bonded to an oxygen, but additionally it specifies it needs a context of a benzene ring to transition to another motif. Meanwhile, motif 183 is a benzene ring with 3 possible contexts, 2 of which specify a single oxygen. Thus, motif 5 can use the benzene ring in motif 183 to satisfy its context, and motif 183 can use the oxygen in motif 5 to satisfy its context, so the two can snap together like Lego blocks. At a high level, we can match two motifs A and B if a few criteria are satisfied. The first is that a part of A's base fragment is isomorphic to one of B's contexts. And 2, a part of B's base fragment is isomorphic to one of A's contexts. And 3, A's context and its base is isomorphic to B's context and its base. And 4, A's context and its base, which is isomorphic to B's context and its base, is connected. This allows us to add 2 production rules to our grammar, namely that any occurrence of A can be replaced with A composed with B, and any occurrence of B can be replaced with B composed with A. These are formalized using language of context-sensitive graph grammars, and we refer you to our paper for more details. We match every pair of motifs in this way, and the result is a motif graph where each present edge explicitly describes how you would attach 2 motifs to form a new composite structure. Now, we can represent molecules as derivations of this grammar. Each valid derivation of the grammar can be converted to a random walk over this motif graph. In this example, we see the random walk for this molecule begins at motif 56, then proceeds left to 9, left to 71, up to 70, up to 5, down to 71, down to 70, down to 71, down to 18, up to 71 again, left to 70, and left to 5. Note that we use a colon to differentiate a new duplicate from a revisit. This has also a graph theory interpretation, which is that the random walk has to be an Euler path of an edge-induced subgraph of the motif graph. So after we convert our dataset to a set of random walks over this graph, we can learn the transition probabilities of walking over this graph. This involves two key ideas. The first idea is to model a random walk using heat diffusion over the graph, governed by the Laplacian L. Intuitively, this allows us to model random walks as stochastic discrete processes. The second idea is to make this Laplacian learnable and adjustable, conditioned on a set-based memory. We opt to make the raw edge weights W learnable and also add a parameterized linear transformation layer to adjust the edge weights dynamically during the random walk. The adjusted edge weights govern the diffusion over the graph, with a higher weight indicating a more likely transition. In the end, we train these parameters using stochastic gradient descent to maximize the expectation of seeing the random walks in our dataset. The other key innovation is that we can use the grammar-induced representation for property prediction tasks. The idea is that the trainable parameters induce a representation that can be fed into a downstream graph neural network. We call this representation the weighted random walk, and it's actually the artifact of the generative model. We employed a graph isomorphism network on this random walk graph, where each node is a motif and has the node features of the Morgan fingerprint for that fragment structure. We perform some rounds of message passing, aggregate the embeddings, and map it to scalar outputs. By using a shared representation, we can even simultaneously update the parameters of the grammar and the parameters of the property predictor to best serve downstream prediction tasks. Now, let's look at the results for molecule generation and molecule property prediction. For molecule generation, we compare with VAE-based methods and the previous state-of-the-art data-efficient generative model, DEG. We show we generate more unique, novel, and diverse molecules compared with VAE-based methods. We find that VAEs are prone to collapsing to the same set of structures despite sampling from a Gaussian prior. We also compare with VAE-based methods that use larger motifs, and we even endow them with expert-based motifs, but the same problem persists. This highlights the advantages of grammar-based methods in data-efficient settings where there are only as few as 100 examples with large structural motifs that may be difficult to learn without the right inductive biases. Compared with DEG, our method generates significantly more synthesizable molecules, highlighting the importance of integrating knowledge of functional groups as they often correspond to purchasable building blocks. For property prediction, we compare with a wide range of molecular property prediction baselines, including standard GNNs like WD MPNN to motif-based GNNs like ESON or HMGNN. Our method also outperforms fine-tuning pre-trained models like MoClair and UniMo. We are also competitive with GeoDeck, the previous grammar-based state-of-the-art property predictor for small datasets. Despite leveraging expert input, our method is not handicapped in the absence of an expert, since our ablations show that even heuristic-based motifs induce a sufficiently good representation for maintaining comparable predictive accuracy. Compared with GeoDeck, our method is also order of magnitudes more runtime efficient, as well as more data efficient by evaluating after training on only subsets of the dataset. We refer you to our paper for more results and discussions. We also show the performance of our method is not merely due to the use of motifs, but the underlying grammar as well. We compare with a simple bag of motifs baseline as well as a previous state-of-the-art motif-based GNN. We even endow both baselines with our expert annotated motifs. The results show those methods cannot integrate the expert motifs as well as our method and generalize less. Lastly, I will raise two kinds of findings for discussion and analysis. The first is an inherent advantage of our symbolic approach, and this can be generalized. We can scrutinize the learned parameters of our grammar, then find cases where transition probability is close or equal to 1. These correspond to hard grammar rules that our parameters captured from fitting the data. For example, here we find a random walk that visits motif 333 and 393 is guaranteed to go to a duplicate motif 333. When we show this to an expert, they explain that these two symmetrical bromide moieties are indeed a prominent feature of toxicity, which is the property of interest for this dataset. This shows that our model can discover the underlying design rules for these expert-driven domains, and this can lead to new scientific insights. The other kind of finding is an unexpected finding that may not generalize but is nonetheless exciting. We find that the final layer of representations from our property predictor visually form two clusters that correspond to structural subcategories within our dataset. After training, we see that two distinctive visual clusters form, and experts tell us that the clusters correspond to the two primary ways to achieve high photovoltaic properties for this dataset. The structures in the top cluster contain structural features that exhibit high and stable electron delocalization through their orbitals, while the structures in the lower cluster contain multiple ester groups or carboxylates acting as electron donating groups. Meanwhile, other GNN baselines we compared with do not have this qualitative pattern. We believe our grammar-induced representation is responsible for uncovering these secrets of the dataset. As future work, we hope to integrating large language models for automating our workflow further, while incorporating expert knowledge still. One ongoing extension is to teach large language models to reason about the expert level task of fragmenting a molecule. And we can give it some demonstrations and expert reasonings in order to bootstrap this process. Personally, I'm interested in how large language models can induce graph grammars in general, and also how our method can generalize to other domains beyond molecules. I hope you found my presentation interesting, and please reach out if you'd like to learn more or chat further. Thank you.